Hello, this is Subbarao Pinnamneni, Professor with the Department of CSE, Tirupati Institute of Engineering and Technology, Guntur, Guntur, Andhra Pradesh, India. Today I am going to discuss about decision trees, an introduction to it, the first 20 slides, and hopefully it will be recorded. Use a decision tree to predict categories or classification for new events. As you can see in the diagram, use training data to build the decision tree. See, training events and categories and new events, basically training events and new events are the inputs, and category is the output. Generally, for a given decision tree, you'll have category. Most of the time it is Boolean, either yes or no. Otherwise, it may be, but it will be valued to a small number of values. Typically, it will be Boolean, yes or no, true or false. But it can be small number of values. Outlook is equal to sunny and humidity is equal to normal. That classifies as yes, or that categorization is yes. Similarly, outlook is equal to sunny and humidity is equal to high. That classification is no. In this figure, as you can see, the ones in pink border, pink rectangles, are the attributes. The one in blue are the values for these attributes. For example, outlook can take on 3 values. What are they? Sunny, overcast, rain. Similarly, humidity can take on 2 values. What are they? High and normal. So, and the one in yellow, that is no and S, are the classification or categorization. Here it is Boolean value. You have only 2 values, either yes or no. Each internal node tests an attribute. Okay? Outlook is a root node and humidity is an internal node or a child node. Each branch corresponds to an attribute value node. For example, here is pointing to normal. For example, humidity can take on 2 values, either high or normal. So, each branch corresponds to an attribute value node. Similarly, each leaf node assigns a classification. Here the possible classifications are either yes or no. Okay. You see, words can have different meanings in different contexts, and word sense or meaning depends on the context in which it is used. For example, the word run can be used in 4 ways at least. The first way is move swiftly. I ran to the store. Second one is operate. I run a store. That is, he owns a store. The third one is flow. Water runs from the spring. Flow of water. Length of torn stitches. Our stockings had a run. That is, our stockings had torn stitches. So here run has been used in 4 different ways. The first one is move swiftly, the second one is operate, the third one is flow, the fourth one is length of torn stitches. Categories. Use words and labels to name the possible categories. Here the categories are run 1, run 2, run 3, run 4. Features. Features describe the context of the word we want to disambiguate. Features describe the context of the word we want to disambiguate. Features describe the context of the word we want to disambiguate. Possible features include near. Is the given word near an occurrence of word W? For example, here there are 3 features for the word. One is near, the second one is POS, third one is left. You can have more, but these 3 are the features. Okay? Generally, features are the attributes. For example, here POS, near stocking, near race, near river. These are the attributes or features. Noun, verb, yes or no. These are the attribute values. And run 1, run 2, run 3, run 4 are the classification or categorization. So we need to understand this. For example, there are 4 features in the above decision tree. The first one is POS, the second one is near race, the third one is near river, the fourth one is near stockings. The ones given in blue, it's a blue background, are the attribute values. POS, near race, near river, near stockings are the attributes. And word sense, that is the classification. Suppose POS is a noun, it is used as a noun, and it is not one of the 3, then the classification is run 4. Similarly, POS is a verb and it's none of them, then it is run 1. If POS is a verb and if it is near river, then it is run 3. If POS is a noun and it is all of the 3, then it is run 4. Like that we can describe the other ones. You can see it for a minute. This is a partial decision tree. Here, decision trees can be described as disjunctions of conjunctions. Decision trees can be described as distinctions of conjunctions. Outlook is equal to sunny and wind is equal to weak. It classifies as yes. Outlook is equal to overcast. It classifies as no. Outlook is equal to rain. It classifies as no. Outlook is equal to sunny and wind is equal to strong. It classifies as no. That is, tennis is not preferred when the outlook is equal to sunny and wind is equal to strong. Tennis is not recommended. Similarly, when outlook is overcast, it is not recommended. Similarly, when outlook is equal to rain, it is not recommended. Outlook is equal to sunny or wind is equal to weak. The complete expression in this case is something like this. Outlook is equal to sunny or outlook is equal to overcast and wind is equal to weak, or outlook is equal to rain and wind is equal to weak. Okay? This is a XOR expression. Sunny and wind is equal to weak. Decision trees represent disjunctions of conjunctions. I've already told for this. Outlook is equal to sunny and humidity is equal to normal, or outlook is equal to overcast, or outlook is equal to rain and wind is equal to weak. Okay? So it is the disjunctions of conjunctions. When to consider decision trees? Instances describable by attribute value pairs. Target function is discrete valued. Disjunctive hypothesis may be required. Possibly noisy trading data. See, instances is describable by attribute value pairs. Typically, a decision tree consists of an attribute node or an internal node or a root node and a value node. That branch contains the value. Okay? Target function is discrete valued. Typically, decision trees are used when target function is discrete valued. However, they can be used for real valued also, but it's rarely used. Typically, they are used when it is discrete valued. Disjunctive hypothesis may be required. Disjunctive hypothesis may be required. You see, these decision trees naturally represent a disjunctions of conjunctions. So when disjunctive hypothesis is required, decision trees are one of the best options. And training data can be noisy. If training data is noisy, also decision trees work well. Missing attribute values. Missing attribute values. Suppose if some attribute values are missing, then also the decision tree works well. The examples include medical diagnosis, credit risk analysis, object classification for robot manipulator. Before I close this slide, I want to tell you one thing. The finders and candidate elimination algorithm that we discussed earlier were not immune to noise, but decision trees are immune to noise. Okay? See, here in ID3 algorithm, we do what we call we calculate what we call entropy and information gain, and whichever has the highest information gain takes that node. The rest of the attributes are again calculated for the information gain, and whichever is having the highest value will take the new node. Like that, node by node, the decision tree is built, and we find the we can build the decision tree. ID3 is used to build decision tree. Sort training examples to leaf node according to the attribute value of the branch. If all training examples are perfectly classified, stop, else iterate over new leaf nodes. For example, which one will take the root node? Will the one with 29 plus 35 minus take the root node? Which one will take the child nodes? 21 plus 5 minus, or 8 plus 30 minus, or 18 plus 33 minus, or 11 plus 2 minus. You see, S is a sample of training examples. P plus is the proportion of positive examples. P minus is the proportion of negative examples. Entropy measures the impurity of S. Minus P plus log 2 P plus minus P minus log 2 P minus. Entropy of S. Expected number of bits needed to encode class of a randomly drawn members of S under the optimal shortest length node. Y. Information theory, optimal length code sign. So the expected number of bits to encode of random number of S. Information is given by that formula. For example, for the two cases, we find that the one with the left case has the highest information gain of 0.27, higher information gain of 0.27, whereas the one on the right has lower information gain of 0.12. So the one on the left takes that node. So that takes the node. So you can see, if it is true, we get that classification. If it is false, we get that classification. Similarly here, that is the next. There are total 14 examples. There are two values, one is high and another is normal. When it is high, how many values are S? I can calculate 3. How many values are no? I can calculate 2, 3 and 4. You can see here is 3 plus 4 minus. Entropy is 0.985 and information gain is 0.151. It is having higher information gain when compared to wind. So humidity takes the second internal node and wind takes the one after that. Outlook has the highest information gain, so it takes the root node. Okay? I'm not showing the calculation in a separate class. I'm going to tell you the calculations. See, for Outlook it is 0.247, for humidity it is 0.151, for wind it is 0.048, and for temperature it is 0.029. So for it is decided that Outlook has the highest information gain, so it takes a root node. Here S denotes the collection of training examples. Okay, this is all. I stop here. Thank you.